Hey, my poster is going to be about the phenomenon of traveling waves recorded in the prefrontal cortex during working memory tasks. Traveling waves essentially refer to the sequential activation of adjacent neuron groups, which gives it the appearance of a moving peak of activity, which kind of is similar to a stadium wave where nothing is actually moving, but the sequential rise and drop of adjacent groups gives it the appearance of a traveling wave. So this is kind of plotted through by plotting the LFP traces across adjacent recording sites. And you can see that the peak of the LFP oscillations are phase shifted in time, which gives it the appearance of a traveling wave. Traveling waves have been shown to be functionally relevant in behavior and cognition. For example, I'm just taking one study out of Terence-Sanowski's group where they show that rotating waves assist in memory consolidation during sleep spindles. We were interested in what traveling waves were doing during working memory tasks. Our task was a simple delayed mass to sample, where there was a center fixation, then a sample object was shown for around half a second. There was a blank delay, and then the subject was tested and had to suck out towards the remembered object. Here I'm plotting the LFPs recorded on the array. Each tile denotes the one recording electrode, and the colors denote the LFP amplitudes. These LFPs are filtered in the beta frequency range. You can see that the LFPs peak near the top right of the array, but then they slowly shift towards the bottom left. This is exactly what a traveling wave looks like, where it kind of moved from the top right of the array and then slowly shifted to the bottom left. And this is very clear when if you look at the phases of the oscillations, you can see that there's always an increasing phase gradient in the direction of the traveling wave. This is the hallmark essentially of traveling waves, where there is always a phase gradient increasing in the direction of wave propagation. And traveling waves are quantified by quantifying these phase gradients. What we did was we used something called the circular correlation coefficient, which was essentially the correlation between the phase map that I just showed and a rotation map around a particular point on the array. What we show is that based on the choice of point, you can get a good estimate of the wave vector. So, for example, like if the wave is going from bottom left to the top right, like the central correlation coefficient denotes a high value, but a different correlation coefficient denotes a lower value. And if a wave rotated around a point, it records a different set of values. So in this way, we show that if you choose like 3 points on the array, these are the 3 points that we chose, the correlation maps that they provide show a unique fingerprint-like signature for each wave type. And these correlation maps we calibrated using simulations, and you can see that each wave type had its own set of correlation coefficients. And based on this, we classified the wave patterns that were observed in the prefrontal cortex, and we saw that rotating waves were the predominant wave type. I'm showing you just the beta frequency band, but this was true across alpha and theta as well, where during baseline or during task performance, rotating waves were the preferred wave pattern on the array. This video is an example of a rotating wave. I'm showing you LFP amplitude filtered in the beta range. You can appreciate that they're going round and round as the form of a rotating wave. The waves did not rotate in random directions. They had a preferred axis of rotation. What we observed was that they rotated like in a back and forth manner. They had always had a preferred axis of rotation. And this was true across all 3 frequency ranges and during baseline and test performance, that they either rotated this way or that way. Not only that, these rotating waves also showed some sort of clear directional modulation during task performance. This was especially true for beta waves. What I'm showing here is the directions recorded during a certain period of time. The red curve denotes the directions recorded during baseline, and the green curve denotes the directions recorded during that time period. So for example, when the sample was shown, that is when the task started, you can see that the directional preference is switched, and it starts preferring the positive directions more and the negative directions less. And it holds this preference throughout the delay and releases it only after the test is over. So the quantification is presented below, where you can see that the positive and negative directions denoted in red and blue, they're around baseline, but when the task begins, the positive directions are preferred while the negative directions are suppressed. And this is held throughout the task in the beta frequency range and released after the test is over. The other two frequencies also showed some directional modulation, but they were not as consistent as the beta traveling waves. But this also kind of goes to show that the three frequencies, the traveling waves in these three frequencies could travel in their own directions, and they did not have to do the same thing. So overall, our hypothesis is that there are maybe two oppositely rotating waves in the prefrontal cortex, and based on where your array is positioned, you're recording either a part of the wave or the whole wave. And not only that, one of the waves is enhanced during the task and the other direction is suppressed. What this means functionally is something that we're actively exploring right now. Rotating waves have been shown to encode information through spike time-dependent plasticity. Traveling waves have also it's been suggested that they can provide a mechanism to track time. And also there have been studies that shown that this sort of reversing wave directions can be a mechanism to differentiate between sensory and predicted inputs. So that is our study so far. With that, I'd like to thank the funding agencies and the lab, and thank you.